Hello, my name is John Muskoff, and I will be going over my nutcracker design analysis and critique for design for manufacturing and assembly. Some of the goals were to reduce costs by 50% by utilizing principles learned throughout the course, and these costs can be reduced by analyzing and making changes to, but not limited to, material selection, reduction in tooling costs, reduction in cycle time, and reduction in parts or parts count. So we started off by doing an analysis of the current design. An analysis showed that the write and return sides were oversized. There was a lot of extra material being used that didn't really serve a purpose. The unnecessary contours in design were the curvatures in the stainless steel plates that were 4.5 inches thick. And this also showed some narrow passageways that could possibly have nuts bind up in them, or could even possibly crush fingers. When we looked at the process sheets, we noticed there was a lot of outsourcing being utilized, which led to a lot of increased cost and wait time. And I noticed that the entire design used 304 stainless steel, and that would be really heavy. The stainless steel is a lot more expensive than other materials like aluminum, and it's also really hard to machine, which is why a lot of it had to be outsourced to water jet. These were some of the areas that we wanted to improve to hopefully lower the cost quite a bit. And after looking at the design and analyzing that, we went ahead and moved on to the current design cost analysis. I went through all of the process sheets and added up the prices and hours it takes to make each part, and on the screen you'll be able to see a summary that showed a total cost of over $4,000 per assembly per part. So you have to sell each nutcracker for at least $4,100 roughly just to cover the cost it takes to assemble it. This showed a couple really heavy areas, and that was included in the right column where you can see cost per assembly. And as you can see, 40% of the cost was on the right side, and another 40% of the cost was on the return side. And this was because it's a big 4.5 inch plate, and it's very costly in both material and outsourcing, which really caused it to cost a lot of the overall assembly. So that's just a rough overview of the cost analysis and some of the areas that we wanted to focus on and improve, along with the aforementioned design issues, which we'll go ahead and move on to now. We'll start with the fact that the write and return sides are oversized. So as you can see on the screen, the circled areas it's really massive. There's a lot of steel being used here that doesn't need to be used. The part of this component that needs to be structurally strong is the side panels, as the drive shaft is connected to bearings that connect to the side panels, the cover plates. So the return and right side are really over designed, and they just utilize a lot of material that I felt needed to be removed. The next issue was the unnecessary contours in the design. Keep in mention that this is all inside the nutcracker, so no one actually sees these contours, and really they just make a very small gap between the wheel and the wall, which could possibly cause nuts to bind up. As a nut passes by the pinion, if it were to get pressed and stuck inside the wheel, it could possibly bind up and really make it hard to turn the wheel. And these contours being so close to the wheel are not only unnecessary, but also decrease the functionality of the machine, and I wanted to remove them. To touch on that, the narrow passageways, that's where the bindings could occur, and to go along with the functionality issue, if someone were to stick their fingers in here, then there's only about 1/4 inch between the wheel and the wall in the current design, so it could crush a finger pretty quick, and it really only becomes a problem if you were to hook up a motor to the drive shaft, and in that case you could accidentally put your hand in the return side, which would quickly pull your fingers in, or also on the top side where the narrow passageway before the walnut gets to the pinion. These are both safety concerns and functionality concerns, and they needed to be corrected. To go along with that, I wanted to touch on the materials being used. I did notice that the entire machine was being made of 304 stainless steel, which is totally acceptable by UNF standards, but I did want to look at some other materials that could possibly be more cost effective. One of the materials I found readily available on my master car was 6061 aluminum plates, and 6061 aluminum is mentioned in USDA guidelines for fabricating and assembly of food processing equipment for dairy, which is actually more caustic to the materials than the walnuts. Dairy is very acidic, which I felt made the aluminum very suitable for this project, and as well as it did meet most of the, or all of the UNF guidelines. Some pros of changing any material. I mentioned the return side. That is the chosen part that I decided to change, because the strength in this part is unnecessary, as the plates are the component that require the structural integrity. So some of the pros of changing the return side were the material would cost a lot less. By ordering in 2-inch thick plates, we actually don't need to outsource anything. The mill can handle that, and it's aluminum, so it's much easier to put in the mill. The material shipping will be much lower, and it's as I mentioned, it's just much easier to machine. It's a lot easier on the mill. Tooling will last much longer, drilling holes into aluminum and milling slots and geometries into aluminum plates versus stainless steel. Some downsides of the aluminum are that more total parts are being made, which could possibly be seen as an issue because assembly may take slightly longer. End assembly. And the machine will also be, since it will be lighter, the machine will also be less sturdy on a countertop. It will actually be slightly front heavy, which was only encountered towards the end of the design. So it is suggested that some alterations be made to where the newly designed nutcracker can be bolted to a countertop. And then I did want to mention at the bottom, as you can see, the 6061 aluminum is roughly a third of the density of stainless steel. So just by simply changing the entire return side, that's already going to it's already going to decrease the weight of the entire assembly by, it's estimated to be about roughly 50%, because of the size of the return side, which actually moves us on to the new design that I used aluminum plates for, shown on the screen now. This is a view from the rear cover. As you can see, the return side was completely replaced by a top, a bottom, and a left side, and it's flipped in the image because we're viewing it from the rear, but so the left side and the top and the bottom are all made from the same aluminum 6061 plate that's 2 inches thick, and as you can see, the right side was also redesigned so that it removed all of the contours. It opened up the interior of the box a lot more. I felt that this was much more suitable for what we were aiming for. There's more space for fingers not to get caught and crushed. It improved the space by at least double, to roughly at least half an inch. It did improve the safety and improve the functionality, which I will explain later. And then the right and return sides also use far less material. By designing this around 2-inch plate, I was able to almost eliminate almost all of the scrap and waste material that was being made in the previous processes, as well as lower the total weight of the entire machine. So moving on to the actual new functionality features. So now that I was explaining that after it was designed, around 2-inch plates of aluminum, we were able to machine all of the parts in-house and remove the water jetting from the right and return sides, which are now the left, top, and bottom. But all of the parts are now machined in-house, other than the wheel and the cover plates, which I will touch later. But as you can see here, the flats were used so that we don't have to use any specialized CNC programming. Everything can be done with basic geometry, and all functionality of the machine is still in place. The open interior actually allows for the wheel not to bind, so it should allow for the user to be able to turn the wheel with a more steady rate and pass walnuts by the pinion and crack them quicker, which should improve the functionality mentioned here. As you can see, the left side, we've increased the gap behind the pinion. The pinion is held in place by the bearings, so the gap behind it didn't need to be so tight, and the gap now will allow the pinion to turn freely and hopefully crack nuts a little quicker. The top, the left and the right side are the increased openings. The top actually was opened up by another 2 inches, and originally being 1.5 inches, the top is now 3.5 inches, and by doing so, this creates somewhat of a hopper so that you can fit roughly 15 walnuts in the top and then turn the wheel to crack them all. And by making that larger, we were also able to move it closer to the side where it allows the walnuts to fall directly where they're being cracked by the pinion. As the wheel turns, the openings will pick up the walnut just before the pinion, and it'll crack it and drop it directly below. And we made the opening in the opening on the bottom smaller so that the nuts should come out on a nice neat pile. After redesigning everything, I did create new process sheets for each of the parts, as you can see here. And I also went ahead and redesigned the cover plates process sheets. I did away with the large material order and found some 12 by 12 by ½ inch plates on McMaster. These ½ inch plates quote a tolerance of plus or minus 0.055 inches, which should be plenty fine for the cover plates. This allows us to order the materials much easier. We can order, we don't have to order 32 units worth of material for one process. We can order, let's say we need to make 10 nutcrackers, we need to make 100. We can order 10 plates, we can order 100 plates. The order management is much easier, and this also removes all needs for water jetting, and that lowered costs greatly. As you can see here, it lowered water jet costs by $2,000, and it also lowered the total part cost by, I think, material cost by roughly $20. And to go along with that, we did a new design cost analysis. All the other parts were left alone. I felt that we had saved enough at this point, and I did a new cost analysis to find that the total cost of assembly was dropped to $981. As you can see here, the big heavy hitters now are the covers, the right side, and the wheel. The wheel is the one part that we still need water jet for, and the covers and right side are roughly the price they are due to the fact that they are all made of stainless steel. The parts that cost the most are made of stainless steel, but this material was found to be very suitable for the components and their purpose in this machine design. So in conclusion, there was a 76% cost saving. That was far greater than the 50% cost saving we were aiming for. And to further touch upon the design, I did want to mention that a DC motor could be hooked up to the drive shaft, and if so, the nutcracker itself should be bolted to the tabletop. This was estimated at an additional cost of around $10 to each part, the bottom part, which in turn added roughly a total of $10 to to the overall cost of the assembly and only increase the total cost of the new assembly by roughly 1%. If you have any questions, please feel free to post them in the discussion forums below. Thank you.